Hello everyone and welcome to our lecture covering the topic of power series. Now you might recall that we saw the Maclaurin polynomial of degree n for the function e to the x, and it was equal to this polynomial 1 plus x squared over 2 factorial all the way out to the degree n term, x to the n over n factorial. So that was the nth degree Maclaurin polynomial, and it's a finite polynomial. But if you keep going with the same pattern, you obtain an infinite series, and we'll be calling these kinds of infinite series as power series. So a power series in the layman's term is nothing more than an infinite polynomial. Okay? And we observe a lot about that infinite series. 1 plus x squared over 2 factorial all the way out to x to the n over n factorial and onwards. Okay, you keep going out to infinity. Well, we can prove that it converges for all x using the ratio test, and that's a tool we'll be using quite a bit in this lecture. So, let's take the limit of successive terms a sub n over a sub n plus 1 divided by a sub n in absolute value, and we took the limit as n goes to infinity. Okay. As n goes to infinity. The nth term will be in the numerator. Okay, so it's x to the n over n factorial. And in the numerator, we have the next term. So that would be x raised to n plus 1 divided by n plus 1 factorial. And then we did some simplifications here. All the x's cancelled except for x in the numerator, and the factorial simplified to n plus 1 in the denominator. And that limit as n goes to infinity is 0. Because again, x here is a constant. It's the n that is going to infinity. And because that limit is 0, okay, the ratio test says that it converges for all x. Okay, remember how the ratio test goes? Okay, you form the limit of successive terms. And if that limit is less than 1, you have convergence. It's in fact absolute convergence. And if it's greater than 1, then you have a divergence. And if it's equal to 1, it's inconclusive. That means you have to analyze the series in a different fashion. Okay? So, this infinite polynomial, this power series that we have just analyzed, show that it converges for all x. In fact, this one is a representation of our exponential function e to the x. And all our other functions have similar types of polynomial representations. So, infinite polynomial representations. And these infinite polynomials we call power series. So, power series is our focus for this lecture. What then is a power series? Okay, so what's the formal definition of a power series? So, well, if x is a variable, then the infinite series of the form, let's say, b sub n, okay, let me magnify, okay, b sub n, x raised to n, where n is equal to 0 to infinity, this is what we call a power series. And this one is centered at 0. Okay? But you could also have a power series centered at some other number, say c. Okay? And it would look like b sub n x minus c to the n power. So it's kind like shifted polynomial. So this one is a power series centered at an arbitrary number c. Okay? So here are some quick examples of power series. The first one, but we have seen this before, x to the n over n factorial. is 1 plus x squared over 2, and so on. What are the coefficients here? The b coefficients, okay, are b sub 0, okay, b sub 0 is equal to 1. B sub 1, what's this number here, is equal to 1. B sub 2, this is 1 half. Okay? B sub 3 is 1 over 3 factorial or 1 over 6 and so on. So these are the coefficients, okay, of our x terms. And this is the, okay, power series centered at 0. But here's another power series. Okay, negative 1 raised to n plus 1, x plus 1 rather, okay, times x plus 1 to the n power. So let's write out the first few terms here. When n is 0, okay, when n is 0, this one is also 0. This is 1 times 1, so we have 1. Okay? Because negative 1 to 0 is 1, and x plus 1 to the 0 power is 1. So it's 1. Then minus x plus 1. Okay, plus, okay, plus x plus 1 squared minus x plus 1 cubed, and so on. So it's an alternating series, isn't it? Okay, where is this power series centered? Remember the formula? X minus c. Okay? And this one is x plus 1. But we can write that as x minus negative 1, which means that c must be negative 1. Okay? So here is another power series. Let's look at another power series here. The geometric series, 1 plus x squared plus x cubed up to infinity. And we often saw this with the letter r. Okay? In the previous lectures, we make use of letter r. But it's the same thing with the letter x. Okay? So this one is an infinite polynomial in x, and it's centered at 0. Okay? It's centered at 0. So we could ask the obvious question, for what values of x does this series converge? For instance, does it converge at 1? Okay? At 1. So that would be when we replace x with 1, 1, 1, 1, 1. Okay, 1 squared 1, 1 cubed 1. So it's all 1 plus 1 plus 1 plus 1. Okay? So that would be 1 plus 1 plus 1 plus 1. Okay? So it diverges. Okay? Because the sum would be infinite, endless rows of ones. Or if we use the n-term test of divergence, the terms do not tend to 0, therefore the series diverges. How about when x is equal to 0? What about at x equal to 0? Okay? So it will be, when x is 0, then we have 1, then this one 0, 0 squared 0, 0 cubed 0. Okay, so it will be reduced to 1 alone. Kasi it will be 1 plus 0 plus 0 plus 0. So it's equal to 1, and therefore it converges. The sum is equal to 1. It converges to a finite number which is equal to 1. So it's reduced to 1. Okay? So how about at negative 1? What about at negative 1? So when x is negative 1, 1, okay, negative 1, negative 1 squared, positive 1, negative 1 cubed. Okay, negative 1, so it's 1 minus 1 plus 1 minus 1, and so on and so forth. Okay, so this one diverges because the terms again alternate or bounces between positive 1, negative 1. And by the n-term test of divergence, the series diverges. So, diverge at x equal to 1, converges at 0, diverges at negative 1. How about at 1 half or 1/3? Okay, what about at 1 half? So let's see. At x equal to 1 half, okay, so 1 half, or 1 rather, plus 1 half, plus 1 half squared, plus 1 half to the 3rd power. Oh, this is our geometric series, yes? and in which r is equal to 1/2. And you already know the answer. If r is equal to 1/2, what did we say? The geometric series converges. So it converges at 1/2, it diverges as -1, it diverges at 1, and it converges at 0. Okay? But the ratio test will also show it. So let's do the ratio test. So we would take again the limit of the absolute value of successive terms. So it will be x, okay, to the n plus 1 over x to the n. We take the ratio, absolute value, as, and then we get the limit as n goes to infinity. So it's the limit of the absolute value of x as n goes to infinity. Why x alone? Because when this is simplified, x to the n times x over x to the n, this cancels out, so we're down with absolute value of x. Okay? So the limit equals absolute value of x. But we go back to the ratio test. What does the ratio test say? It says that it will converge if that limit is less than 1. Okay? So it converges when the absolute value of x is less than 1, which is the interval -1 to 1. So in the number line, it's from -1 to 1. Okay? So this is the interval from -1 to 1. And it diverges outside. Okay? It diverges outside this interval. So, to okay, -1, +1. Here, it diverges. It diverges on outside the interval. Okay, the absolute value of x is greater than 1. And it also diverges at the endpoints. Okay, it diverges at the endpoints at x equal to 1 and at x equal to -1. We have shown that a while ago. Diverges at x equal to 1, diverges at x equal to -1. So it diverges at the endpoints. Okay, so that's something we have to keep in mind. Okay, those endpoints at 1 and -1. So we already observed that it diverges at the endpoints. So this geometric series converges for the absolute value of x less than 1. And we already knew that from our previous study of geometric series, diba? We said last time that the absolute value of r must be less than 1, and which implies that r must be greater than, okay, 0 but less than 1. Okay, greater than -1 rather, greater than -1 but less than 1. Okay? Greater than 1 but less than 1. Greater than -1, I should say, but less than 1. So, in fact, we know even more. We know what it converges to. Okay, in fact, we know the sum of this. Okay, that the sum of this series is in fact 1 over, okay, 1 over 1 minus x. And we know what it converges to. So, it's 1 over 1 minus, okay, 1 over 1 minus x. So, we have represented actually the function 1 over 1 minus x with a power series, okay, with an infinite polynomial. But this is only valid on this interval, okay, from -1 to 1. But there's a nice way of summarizing our results with a picture. So this series was expanded about 0. Okay, so you write the number line, we draw the number line, and we indicate 0. And then the interval of convergence was from -1 to +1. So it was an open interval. Okay, an open interval because it wasn't converging at the endpoints. And so we say that the radius is half the length of this interval. Okay, so it's the length from 0 to 1 or from 0 to -1. So we say that the radius of convergence is 1. Okay, and the interval of convergence is from -1 to 1. So it's an open interval. So this is a nice way of expressing the concepts that we have just discussed. Okay, so let's study another power series. This time another infinite polynomial in x. So here it is. It's n factorial x to the n from n equals 0 to infinity. So let me write out the first few terms so that we will get comfortable with this new example. What are the first few terms? Okay, so 1. The first would be 1. Okay, remember that 0 factorial is equal to 1 and that x raised to 0 is also equal to 1. So it's 1 plus, when x is 1, 1 factorial 1, x to 1. So x, 1 plus x plus 2x squared plus 6x cubed plus 24x to the fourth. So notice that the coefficients are getting bigger and bigger. Okay? Because the coefficients are n factorial. Okay? So what comes after 24? It's 120. Okay? So let's see where it converges. Okay? So we know that this one will converge at 0. All these power series converge at a point about which you're expanding the polynomial or the infinite polynomial. Because if you plug in x equals 0, what happens? When you plug in x equal to 0, 1, 0, plus 0, plus 0, plus 0, nag-collapse siya into 1. Okay? It collapses to 1. So the real question is, does it converge anywhere else? So let's find out using the ratio test. Okay, so we take again the limit of successive terms. The denominator would be n factorial x to the n. What about the numerator? It's the next term. N plus 1 factorial x to the n plus 1. And then we do the usual simplifications that we did in the previous. Now all x's will disappear. Yan. X to the n will cancel out and factorial will cancel out. Okay? So all the x's will disappear except for an x in the numerator. May maiiwan na x in the numerator. And also the factorials cancels out. But now the n plus 1 is in the numerator. So now we have the limit as n goes to infinity of the absolute value of n plus 1 times x, where x, remember, x is fixed. Okay? X is fixed. So what is the limit of this then if x is a fixed number? And as n goes to infinity, this gets increasingly big that it grows to infinity also. So the limit is infinity. So as n grows, it's infinity. Okay? Except, of course, at x equal to 0. Okay? What did we say a while ago? It collapses at x equal to 0. It collapses to 1. So it converges at x equal to 0. But in general, this in fact is getting bigger and bigger and bigger. It's growing. So where does it converge? Okay, the ratio test says that if you're greater than 1 and if you're infinity, you diverge. So this series only converges at one point. Okay? So this is a worst case scenario. It converges only at a single point. And that point is 0. Okay? So let's take back a moment. So we have seen here 3 examples with 3 different kinds of convergence. The first example was x to the n over n factorial, and that converged for all x. Then we also saw x to the n, the geometric series, and it converged on an open interval. It's a finite interval, -1 to 1. And it happened to be an open interval. And then we saw in the last example, which converge at a single point, only at x equal to 0. So these are 3 possibilities. So in the first case, we say that the radius of convergence is infinity because it converges everywhere. And in the third case, the radius is r is equal to 0 because it only converges at a single point. But at the middle, so this is the best case. Okay, the middle has a positive radius of convergence. Okay, so here's what the theorem say about that. So suppose you have a power series centered at C, then one of the three things is true. It could be that it converged only at C, like in the third case, and we saw that in the third, or the best of both worlds, or all worlds. I mean, best of all worlds. It converges absolutely everywhere, or for every x. Okay? It converges everywhere. Or, in the third case, most interesting case, when there exists a real number r greater than 0, okay, r is the radius of convergence, such that the series converges as uh, it converges absolutely, rather, for x value satisfying x minus c is less than r. Okay? It converges absolutely for absolute value of x minus c less than r. And it diverges outside, or when the absolute value is greater than r, or outside the radius. Okay? And we have r here is the radius of convergence. So for values at the endpoints here, you have to check with further analysis or with further study. Okay? So do not forget r is the radius of convergence. So this is the picture of what we're talking about. Okay, in one case, you might have just a single point of convergence. So just a single point of convergence, C. So let's name this to be C. The next case is, I think, the best because it converges everywhere. Okay, it converges on the entire real number line. Okay, and this is most interesting case. It converges on a little interval around the radius. Okay, around C of radius R. So it converges up to C plus R and down to C minus R. And it might converge at the endpoints. It may not. That we'll see, okay, with further study. And then we'll see some more examples in the succeeding slides. Okay? Okay, so let's do another example. Let's see how to illustrate the theorem we have just discussed. So here is a power series, okay? 3 times x minus 2 to the nth power, where n is from 0 to infinity. Okay? So this one is a power series centered at 2. Okay? X minus c. So it's centered at 2. The question is, where does it converge? And what's the interval of convergence? How about the radius of convergence? Okay, so here we go. Just like what we did in the previous, we take the limit of successive terms, apply the ratio test. So we take the limit as n goes to infinity of a sub n plus 1 divided by a sub n in absolute value. Okay, so the bottom part would be 3 times x minus 2, okay, to the nth power, while the numerator would be 3 times x raised to 2 raised to n plus 1. Okay? Then we can cancel out 3's right away. Okay, this one will go away. And x minus 2's simplify just to the absolute value of x minus 2. So after simplification, we're left with absolute value of x minus 2. Now, when we take the limit as n goes to infinity, okay, so here there's nothing to do. N is not in the resulting limit. There is no n in this expression, but we only have x. Okay, so the answer is the absolute value of x minus 2. So this one is considered a constant. So it's the absolute value of x minus 2. Now, how do we interpret this answer? Well, again, we go back to the ratio test, okay, that we have a convergence if the absolute value of x minus 2 is less than 1, and we have a divergence if the absolute value of x minus 2 is greater than 1. Okay? But it does not say anything about the endpoints. So we have to look a bit closer at the endpoints. Okay? But we already know that the radius is 1. Remember, r is 1. Okay? R is equal to 1. The radius is equal to 1. Okay, so what the question is, it's an interval of length 2. Okay, so this one is an interval of length 2 since the radius is 1. So centered at 2. So 1 unit to the right, 1 unit to the left. 1 unit away from 2 on the right, and 1 unit away from 2 on the left. So this must be 3, and this must be 1. Okay, so the endpoints are at 1, 3. The question is, does it converge at the endpoints? So let's find out. Okay, so the endpoints are at 3 and 1. So when x is 3, so let's see what happens to the series when x is equal to 3. When x is equal to 3, so 3 times x is 3 minus 2 to the n power. But this is reduced to 1 raised to n, and 1 raised to n is equal to 1. So 3 times 1, so it's summation of 3. Okay? So it's summation of 3. So this will be just 3 plus 3 plus 3 plus 3 plus 3, and this one diverges. Okay? Because when you add this up, it will give you, okay, large sum. Okay? The sum increases as we move out to infinity. So this one diverges. How about at x equal to 1? What happens? Okay? What happens when x is equal to 1? So 3 times 1 minus 2. Okay, but 1 minus 2 is negative 1 raised to n. And we write out the first few terms when n is 0. Okay, 0 raised to n is 1, so 3. When n is 1, so 3 times 1, minus 3. Okay, so it will be 3 minus 3 plus 3 minus 3. And again, this diverges by your nth term test of divergence. The terms do not tend to 0 because it bounces between 3 minus 3, 3 minus 3. Again, it diverges. So, the interval of convergence is the open interval, okay? The open interval 1, 3. Okay? 1, 3. And the radius is 1. It converged 1 unit on both sides of 2, up to 3 down to 1. But it did not converge at the endpoints. Okay? Sorry, at the endpoints, I should say. So, let me summarize these procedures that we just did. We determined the radius of convergence by the ratio test. Okay? Determining the radius of convergence by the ratio test. But then we have to analyze those endpoints to see if it converges there also. And that will give rise to the interval of convergence. So, it was this time open. Okay? It's open, just like in the previous example. Okay? Now, let's move on to the next. So, to determine the radius of convergence, okay, we use the ratio test, and we need to analyze the endpoints, okay, to give rise to the interval of convergence. So, here is another example where it's a half open interval. Okay, let's see. Here is the power series x to the n over n. Okay, so I'll start it at 1. When n is 1, so when n is 1, x raised to 1 over 1, it's x. When n is 2, x raised to 2 over 2. Okay? When n is 3, x cubed over 3. So it's going to be x plus x squared plus x squared over 2 plus x cubed over 3 plus x to the fourth over 4, and so on. Now, let's see where it converges. So, we do the ratio test. Okay, so the denominator would be x to the n, okay, x to the n over n, and the numerator is the next term, which is x to the n plus 1 over n plus 1. And then we apply some simplifications. Okay, after simplifications, all the x's will disappear except for 1x in the numerator. Okay, and then we flip up the denominator. It becomes n plus 1. Okay, and then we take the limit of that, okay, of the absolute value of this expression as n goes to infinity. Okay, so well, what's left here? N over n is 1. So we're down to the absolute value of x. Okay? It's the absolute value of x. So the limit equals the absolute value of x. So, okay, this converges when the absolute value of x is less than 1. Okay? Because that's according to the ratio test. And it diverges, okay, outside, or when the absolute value is greater than 1. Okay? So that's according to the ratio test. But what about at 1? So let's find out. Okay, how about at x equal to 1? What happens when x is equal to 1? So when x is 1, we have 1 plus 1 squared over 2, 1 half, 1 cube, 1 third. Okay, so look, what do we have now? 1 plus 1 half plus 1 third. Isn't it the harmonic series? Okay, isn't it the old harmonic series that we have studied? And you know very well that this diverges by the integral test. Okay, so it diverges at x equal to 1. Now the question is, how about at negative 1? What about at negative 1? What happens there? So now it's negative 1 raised to n over n. Okay? So if n is 1, so negative 1 raised to 1, that's negative 1 over 1. So it's negative 1. When n is 2, negative 1 raised to 2, positive 1 over 2. So it's 1 half. So it's going to be negative 1 plus 1 half minus 1 third plus 1 fourth. So that's the negative of the harmonic series, isn't it? So it's an alternating series, but it starts at negative 1 instead of a positive 1. But does the series diverge or converge? Now, if we make use of the alternating series test, we can show that this converges. Okay? So, it converges at x equal to negative 1. It diverged at x equal to 1, but it converged at x equal to negative 1. So, let's try to illustrate. Okay, so we illustrate it with an interval that's half open and half closed. It converges at minus 1 or at negative 1 and diverges at 1. So it's closed, open, half closed. Okay, converges at negative 1, diverges at 1, and the interval has a total length of 2 because the radius is 1. Okay? And so clearly you can see that determining the radius of convergence is easier than determining the interval of convergence because the interval requires further analysis at the endpoints, and it can turn out to be open, it could be closed, it could be half open, or whatever the possibilities are. So let's look at one more interesting example. Okay, so look at this example. So here is another example. It looks frightening, scary at first glance, but when you write this out in summation notation, so it's n equals 0 to infinity of negative 1 to the n, x to the power 2n plus 1 divided by 2n plus 1 factorial. Okay, so it's a little complicated and it looks awful. So let's write out few terms of the series. Okay? So when n is 0, this is raised to 0, this is 0 plus 1, so x raised to 1. Okay? So this is 1x over, this one is 1 factorial. Okay, 1 factorial, so it's going to be x. X, okay, so the first term is x. What about the second? When n is 1, so negative 1 raised to 1, so that's negative 1. X raised to 2 times 1, 2 plus 1, so x cubed all over 3 factorial. So it's, okay, because of this minus sign, so it's minus x cubed over 3 factorial. And the next would be x to the fifth factorial, or x to the fifth rather, over x to the fifth power over 5 factorial, and so on. Okay? And the second or the third term is with the plus sign. Okay? So it's not scary at all. In fact, you can recognize this. Can you recognize this? Can you guess what this is? Okay? This was given as your quiz in the previous meeting. Okay? If you can remember, the sine function. Okay? So it's going to be sine x. When we shall finish this example, you'll find out that it's the sine function. So I think you can already see that it's going to be sine x. In fact, the first two terms form the third degree, the third degree Maclaurin polynomial for sine x that we have already calculated in the previous lecture. Okay? Now, where does this converge? Okay? Where does the series converge? Well, we've got to use the ratio test, and it's again quite complicated because of the many factors. Okay? So, just the same, we have to take the limit of successive terms, a sub n plus 1 over a sub n in absolute value. Okay? So we have in the denominator negative 1 raised to n, x raised to 2n plus 1 over 2n plus 1 factorial. And in the numerator, the next term, negative 1 raised to n plus 1, x raised to, why is it 2n plus 3? Because it will be 2 times n plus 1 plus 1. Okay? So 2 times 1 here is 2 times 1 is 2 plus 1, so it's 3. Okay? All over 2n plus 3 factorial. And after much simplification, okay? After much simplification, what will this be equal to? Okay, we will be left with the limit of x squared over the quantity 2n plus 3 times 2n plus 2. Okay, all other factorial stuff would disappear. So this is our limit now. Okay, so the limit is x squared, the limit of x squared over 2n plus 3 times 2n plus 2 in absolute value. And then we take the limit as n goes to infinity. Now, I want you to pay attention to the denominator. The denominator, because of the presence of n, heads to infinity. Okay? So, the quotient approaches 0 because this is a fixed number. So, a constant divided by a very large number, the limit is equal to 0. Okay? And so, we say the series converges. This power series converges for all x. Okay? It converges for all x from the ratio test. If the limit is less than 1, then it absolutely converges. Now, you might ask yourself, what do the first few terms of this series look like? The partial sum. So here's a picture of x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial. So it's a partial sum of that power series, partial sum. And it's starting to look like the sine x. So at least around the origin, if you can remember the graph of your sine x in trigonometry. So this one looks like your sine x. But later on, we'll actually prove or illustrate that this indeed converge to sine x. So right now, we know it converges, but it's not clear what function it converges to. But I think you can now see that it's going to be sine x. Okay? So, it turns out that a given power series with certain radius of convergence r, and r might be infinity, and you can differentiate the term, you can differentiate them term by term, or integrate them also term by term, and the radius won't change. The radius will stay the same, okay? The interval might change, but not the radius. So let me illustrate that fact, okay? So with this example, so we'll look at the series x to the n over n from 1 to infinity. We analyzed that and saw that the interval of convergence was the half open, okay, interval -1 to 1. So closed at -1 and open at 1. So now we differentiate that series, okay? We will differentiate the series. What do you get? Term per term. Differentiate. Find the derivative of the series. Okay? So, it's nx raised to n divided by n. Okay? Nx to the n minus 1, I'm sorry, n minus 1 rather. Okay? Nx, so here it is. Okay, nx raised to n minus 1 over n, and what happens to n? It will cancel out. So it will be just x raised to n minus 1. Okay, x to the n minus 1, which is equal to, okay, when n is 1, so x raised to 0, it's 1. When x is 2, 2 minus 1, x. So 1 plus x squared plus x cubed, and so on. So isn't it interesting? The derivative of f of x turns out to be the all geometric series, and it converges on the open interval -1 to 1. Okay? So we lost an endpoint in the process. Okay? We lost the endpoint -1. Okay? So it no longer converges at -1. So, this is what happens when we differentiate. So, we lost the endpoint -1. The resulting series diverges at -1. So, we lost the endpoint. What happens when we integrate? So, let's try to integrate also. What we did a while ago was we differentiated. So, this time, we take the same series which we started with a half open, half closed interval, and let's integrate term by term. Okay? So, let's integrate term per term naman. So, we start from x raised to n plus 1 over, okay, remember? Okay, from here. X raised to, add 1 to the exponent over exponent plus 1. Okay, times n. Okay? So, what happens here? So, the integral would be raise the power by 1, x to the n plus 1 divided by n plus 1. And we already have an n in the denominator. So, we get the summation n equals 1 to infinity, x to the n plus 1 over n times n plus 1. And there's an arbitrary constant here that won't affect anything. Okay, so what does that equal to? The constant x squared, okay, x squared over 1 times, okay, 2 plus x cubed over 2 times 3, and so on. So where do you think this one converges to? Okay, so it's going to converge on a closed interval -1 to 1. So that's actually going to converge at 1 and at -1. Okay, so what happened? So in this example, we gained an endpoint. Okay, we gained an endpoint. So when differentiating, we lose one endpoint. When we differentiated or when we integrated, we gained an endpoint. So we started with this half-open interval. When we differentiated, took the derivative, we lost this endpoint. But when we integrated, we gained one endpoint. But the radius is still unchanged. Okay? The radius is still equal to 1. So in general, if you differentiate a power series, you might lose the endpoints. Okay? You might not, but you might lose some when you differentiate. And you might gain some when you integrate. But again, the radius will not change. Okay? So, imagine you're making up an examination and you want the answer. You want to make up a problem and you know what the answer is. You know what you want the answer to be. You want the answer to be, you want the question to be some power series so that the interval of convergence is -2, 2, and we make it an open interval. So you want the answer to be an open interval from -2 to 2. So what power series would you use on your test? Okay, what test question could you use? Well, there are actually many answers. Okay, but here's a simple one. Use a power series or use a geometric series, but make it x over, okay, x over 2 to the n power. When does this converge? Okay, when does this converge? Well, it's a geometric series. So, from our theorem that the r value, okay, in which case our r value here is x over 2, absolute value of x over 2, okay, that has to be less than, okay, 1 in absolute value. So, x over 2 less than 1 means that the absolute value of x is less than 2. So the interval of convergence is from -2 up to 2, and it's an open interval. Okay? So let's try another problem, another practice problem. So let's look at x to the power x to the n, rather, x to the n over n squared. Okay? So, x to the n over n squared from 1 to infinity. Now, what's the interval of convergence? First, we have to compute for the radius of convergence using our ratio test. And then we analyze the endpoints. Okay, so we take the limit again of successive terms. So, we did the ratio test and the denominator was x to the n over n squared. The numerator would be x to the n plus 1 divided by n plus 1 squared. And then we flip the fractions and simultaneously canceled all x's. So we're left with just a single x in the numerator. Then we have an n squared over n plus 1 quantity squared. And then we ask what happens as n goes to infinity. Okay, as n goes to infinity of the absolute value of this expression. Well, x here is a fixed number. So it's really what really happens to n squared over n plus 1 quantity squared. Okay, n squared and n squared, actually this one goes to 1. So the final limit would be absolute value of x. Okay? So again, what does the ratio test tells us? Okay? What does the ratio test tells us? Convergence if the absolute value of x is less than 1, and divergence if the absolute value is greater than 1. Okay? But I don't know about the endpoints. So let's do the endpoints. So here we go. What happens at the endpoints? So when x is equal to 1. So it's 1 over, okay, 1 over n squared. Okay, 1 over n squared. And remember our P series? So this brings us back the memory of your P series. Okay, this one, when P is greater than 1, it converges. Okay, so the P series test, please do not forget the P series. So this is 1 over n squared P series, and P is equal to 2, and this one converges. How about when x is equal to minus 1? Okay, so about minus 1, it would be negative 1 raised to n over n squared. Now, that's the series you get when you plug in the other endpoint, negative 1. So, it's an alternating series, right? Okay, so we could use the alternating series test and it will work here. So, the absolute value of this converges. So, the series itself also converges. So, we get the convergence at both endpoints, negative 1 and 1. Okay? So, this is the last example.